Okay, welcome back to our Explainer series. Today we're jumping straight into episode 2.2, Canister and Jacking Systems. Picture this, right? You're on a massive drill ship, something like the GF-12,000, and you're floating over 3,000 meters of open ocean. Below you, there are these 6 giant thruster pods spinning away, cranking out 33 megawatts of power just to keep the ship still. But what happens when one of those 5.5 megawatt thrusters breaks down? You can't send divers down, and you definitely aren't heading back to port. It has to come up. Let's get into how engineers actually pull off this insane feat of lifting a multi-ton motor straight out of the water while the ship is still floating.
The economic reality here is just wild. These thrusters are submerged 24/7. They're fighting salt water, currents, marine growth, random debris. Because of all that wear and tear, they absolutely have to undergo serious maintenance every 5 to 15 years. Now, if you couldn't retract them, every single repair would mean disconnecting from the well and dragging the whole ship to a dry dock. We're talking weeks of lost time. And in the offshore industry, that means bleeding millions, literally millions of dollars in lost day rates. So to avoid that nightmare, engineers came up with an ingenious at-sea retraction system. It lets the crew lift the thruster right out of the ocean and straight into the hull.
And the absolute hero of this operation is the rack and pinion jacking system. It's basically a highly precise mechanical lifter. You have a rotating gear, that's your pinion, and it securely meshes with a linear track of teeth, which is the rack. This setup gives you incredibly precise, low-speed movement while handling just unbelievably heavy loads. And look, precision here is everything. It's absolutely crucial. If this system is mishandled, or if those gears fail to hold, you're looking at a multi-ton piece of machinery catastrophically free-falling straight down through the bottom of the vessel. No pressure, right?
Okay, let's dive into this and make this massive nautical concept a bit easier to picture. Imagine the thruster sitting inside a rectangular steel canister shell. This canister works exactly like a vertical drawer built directly into the bottom of the hull. The thruster just slides in and out of it vertically. Honestly, if you've ever looked at the steering system in your car, where turning the wheel moves a gear along a tooth bar to turn the tires, it's the exact same principle. Engineers just scaled it up to an industrial size, flipped it vertically, and made it strong enough to lift a machine the size of a house.
Now, I want you to think about the number 0.5. In a world where we expect our high-tech industrial gear to move fast, the jacking system for this canister operates at a bottom-end speed of just 0.5 meters per minute. That is an unbelievably slow, creeping crawl. To put that into perspective, it would take several minutes just to move this thing the height of an average person.
When you first hear that, it kind of sounds like a frustrating bottleneck, doesn't it? Like, why build such a powerful, massive machine only to have it inch along at 0.5 to 1.0 meters per minute? Well, I want to completely reframe that for you. This incredibly slow crawl isn't some mechanical limitation. It's a deliberate, absolutely critical safety feature. Think about it. You're lifting a multi-ton object inside a confined steel shaft. If it moved quickly, a rapid movement could easily mask a mechanical snag, right up until it violently tears the equipment apart. That slow speed gives the operators the exact time they need to monitor the lift, check the pressures, and catch any faults before a multi-million-dollar disaster strikes.
And this brilliantly illustrates how marine crews mathematically plan for these critical operations. When they schedule a maintenance window, it's a pretty simple formula. Travel distance divided by jacking speed equals total minutes. But there's a major golden rule here. You should always plan the operation using that slower 0.5 meters per minute rate. Even if the spec sheet says it can hit 1.0, the reality of lifting under heavy loads, fighting water back pressure, and dealing with marine growth friction means it's almost always going to be slower. Assuming the worst-case timing ensures things don't get rushed and everyone stays safe. So eventually, this thruster finishes its slow crawl to the top and gets locked into place with a primary lock. But the system also features a completely independent secondary locking mechanism. I'm going to pause right here and actually challenge you to think like a marine engineer for a second. If the primary lock is fully engaged and it holds that massive thruster securely, what is the secondary locking mechanism actually for? Why overcomplicate the whole shebang? Well, the answer comes down to one of the most fundamental rules of deep water engineering. You have to eliminate single-point failures. Think of it like changing a tire on your car. The jacking mechanism and primary lock are basically your hydraulic car jack. It's incredibly strong, sure, but it's mechanical, which means it can fail. The secondary lock acts like the rigid jack stand you slide underneath. It ensures that the massive load is never resting entirely on the lifting mechanism alone.
This belt and suspenders engineering is mandatory out there. If a pin wears out or hydraulic pressure drops, that secondary lock guarantees the unit won't go into freefall. Let's move on and see how this builds into the actual physical procedure. To safely secure this 5.5 megawatt beast, there's a strict, mandatory sequence. Step 1. The jacking system lifts the thruster to its final retracted position. Step 2. You engage the primary lock. Now, Step 3 is where it gets critical. The crew must independently, physically verify that the secondary lock is fully engaged. Only after that verification is perfect can they move to Step 4 and actually release control of the jacking system.
So the crucial point here, and this is a severe warning, is that skipping that secondary lock confirmation before releasing the jacking control isn't just some minor paperwork error. It is a known, documented cause of catastrophic drop incidents across the entire industry. If operators get complacent, they assume the primary lock is holding, release the tension, and then the primary lock slips, there's literally nothing left to catch it. Following that dual lock protocol is, quite frankly, the difference between a routine Tuesday and a catastrophic hull breach.
Okay, so we now understand exactly how the crew can safely pull these massive thrusters up into the ship's hull like giant vertical drawers, using rack and pinion strength and rigorous safety protocols. But this brings up a really fascinating final question. Retracting the thruster is only half the story. When it's deployed, that machine is sitting deep underwater, generating immense heat under crazy pressure and handling its share of a 33 megawatt load. How in the world does a complex electromechanical system survive those brutal submerged conditions without just instantly failing? Well, that requires specialized life support systems for cooling, steering, and lubrication, which is exactly what we'll be breaking down in our next explainer. Thanks for joining me, and as always, keep questioning how the world around you works.